And the last speaker of this session is Haowen Zhang, who's going to talk about the galaxy supermassive black hole connection.
All right, can everyone hear me? People in the back? Okay, thanks. Hi everyone. I am Haowen Zhang, and currently I am a finishing graduate student from the University of Arizona. So today I want to briefly talk about my PhD work, which is this empirical TRINITY model of galaxy versus black hole connection from redshift 0 to redshift 10. And specifically, I want to discuss whether our high redshift AGN predictions match what we see with JWSTs very recently. So black holes are important. We use them in many simulations to quench especially massive galaxies. In observations, we keep finding them at higher and higher redshift. Currently, if confirmed, the record holder will be GNZ11 at redshift 10.6. We have all these different observations. Wait. What? Okay. So we have all these different observations. We measure black hole masses. And we also measure how bright these quasars or accreting black holes are. But if we just look at these data sets separately, it is really hard to find out how black holes evolve in different galaxies or halos, because there are so many degeneracies in each of these data sets. So for example, if you look at quasar luminosities, you may know how much radiation the black holes are giving out, but you really don't know how fast they're growing, because at fixed luminosity, the accretion rate and the radiative efficiency of AGN are totally degenerate. But fortunately, such degeneracies, they can be broken by just putting many data sets together and use them as joint constraints. So the idea here is very similar to what we do in observational cosmology. So we just collect different data sets, which by themselves are pretty degenerate. And if we put them just together, suddenly we can shrink, because they are degenerate in very different directions. We can suddenly get a much better constraint on the amount versus dark matter. Okay, so the idea is to basically use as many data sets as possible and use them to jointly constrain the galaxy versus black hole connection. So why empirical model? Because compared to hydrodynamical simulations and semi-analytical models, it is much, much easier and faster to generate lots of mock universes with galaxies and black holes and compare them with real observations to find the one that best matches a multitude of galaxy and black hole data. And another advantage of empirical model is that they usually come without any assumptions about the underlying physics that's in the galaxy versus black hole interaction, which we typically have to make assumptions for when implementing subgrid physics in simulations. Instead, in empirical models, what we do is that we try to find these empirical relations that match all the data, and then identify, by comparing our empirical relations with all the simulations that we have, identify the viable physics that are implemented in these simulations to reproduce the empirical relations that we found. Okay, so basically what we're doing in Trinity is to reconstruct supermassive black hole growth histories in different galaxies and halos by the joint constraint of many galaxy and black hole data. So from Peter's work of universe machine, we have already know that galaxy assembly histories can be constrained by lots of galaxy data, like galaxy mass functions, galaxy star formation rates. And if we, on top of that, if we add the quasar luminosity distributions in different galaxy mass bins, we can then figure out how much black hole energy, how much black hole radiation is given out by black holes in different galaxy populations at different times. In other words, this is just the black hole luminosity history. But if we want something that's more physical, or in other words, black hole accretion rate history, we can then use this black hole mass versus galaxy mass relation to break the degeneracy. So basically, we are just going to compare the cumulative black hole energy at the end of each luminosity histories with the final, or like redshift 0 black hole mass in different galaxy populations to find out how much energy is generated per unit black hole mass accretion. And if we already solve for this AGN radiative efficiency, we can then trivially convert this luminosity history of black holes into their accretion histories. And finally, if we simply read out the black hole masses in different galaxy populations at different redshifts, we can then directly recover the black hole mass versus galaxy mass relation as a function of redshift. Okay. So in addition to this mass scaling and radiative efficiency, we also model lots of other black hole properties like AGN duty cycle and Eddington ratio distributions in Trinity. So to do that, we have included many data sets, including, in addition to the galaxy data, we have included, firstly, some luminosity constraints like total luminosity functions. They tell us how much total energy is given out by different black holes. Oh, sorry, by all the black holes. And we also use the luminosity distributions of quasars in different galaxies to constrain how this total energy should be contributed by different galaxy populations. And as I said, to break the degeneracy between accretion rate and efficiency, we also need some mass constraints. So firstly, of course, the redshift 0 black hole mass versus galaxy mass relation anchors the total amount of black holes that should be formed by redshift 0. And also, we use some black hole mass functions from AGNs or actively accreting black holes at higher redshifts to specify the amount of mass corresponding to each redshift's black hole accretion. Okay, so if we match all these data, we get the following black hole mass versus galaxy mass relation for all the black holes at redshift 0, and then in comparison with at higher redshifts, starting from redshift 6 all the way to redshift 10. So what we can see here is that the scaling relation evolves much more strongly at the low mass end compared to the massive end. So physically, a few things can happen to and contribute to this evolution. In general, low mass galaxies, they have shallower potential wells. So the first thing that could happen is that supernovae feedback is more efficient to prevent gas from getting accreted by the black holes in low mass galaxies. The second thing, and the second thing that could also have happened is that in the low mass galaxies, black holes actually, because of the shallower potential well, it is easier for the black holes to move around and decrease the amount of gas that's available for black hole accretion. Okay, so this is the prediction for all the black holes. But in real life, we never see all of them because we are always limited by the flux limit of the instruments. So, in fact, if the Eddington ratios of supermassive black holes are similar, then overmassive black holes are going to be brighter because the luminosity is simply a product of Eddington ratio and black hole mass. And thus, overmassive and thus brighter supermassive black holes are going to be more likely to get detected and included in our sample. And what happens is that if we just look at the scaling relation for these AGNs or quasars above different luminosity limits, we will see that there is a bias. The typical black hole masses are going to be biased towards the higher values, and this bias is stronger, much stronger, for the brightest quasars compared to the faintest AGNs. Okay, so do these predictions match our observations? So prior to JWST, we have what we have are basically the redshift 6 quasars that are pretty bright. And they do seem to match what we expect to see at such a bright luminosity. And then here's all the JWST AGN or AGN candidates above redshift 7. So basically, they do have some significant uncertainties in both the galaxy mass and black hole mass. So with all these uncertainties accounted for, I think these predictions are still broadly consistent with what we see in real observations, although the observed black holes here do seem to be a bit more massive compared to what we expected. But to be fair, these Trinity predictions assumes that all the black holes above these luminosities are going to be detected. They're never going to be outshined or covered by their host galaxy's lights. However, this is kind of unrealistic, especially for those low-mass AGN populations. So, especially for these low-mass, fainter AGNs, I think these estimates of the biases should be viewed as basically lower limits. To better model this selection bias entails basically a more careful modeling of galaxy and supermassive black hole SEDs, which I will have to do in a future work. So here it is. Okay. So in the interest of time, I'll just summarize here. In my PhD, I built this Trinity model with all my advisors and collaborators. This is a very flexible and fully data-driven empirical model to understand how black holes evolve in different halos and galaxies. And the main results, firstly, we do see some redshift evolution in the intrinsic black hole mass versus galaxy mass relation, which is stronger at the low mass end. Secondly, high redshift quasars are bias samples to study the black hole mass versus galaxy mass relation, and this bias can be quantified by Trinity. And thirdly, many JWST high redshift AGNs are broadly consistent with Trinity's prediction of the black hole mass versus galaxy mass relation, given their luminosities and measurement uncertainties. Okay, so I also have some preliminary results that I don't have the time to show, so please feel free to ask me about them if you want, but I'll just end here, and thanks for your time. I'll take questions and comments.
Questions?
So you showed, nice talk. You showed, I'm Brant, by the way. You showed a very nice, relationship here for your quasar activity, where the black holes go above the local relationship between M black hole and M star. But if you look at galaxies that are on the M black hole M star relationship at, say, 10 to the 9 or 10 to the 10 stellar masses, is it the case that they never then, at any point in time, have ever had AGN activity with L-bol above, say, 10 to the 46?
So you're saying that, for example, for black holes that are already, they seem to be right now on the relationship, whether they have never been above the scaling relation. Right?
Well, I mean, your plot seems to suggest that if you had an L bowl of 10 to the 46 or higher, you would be, in the black hole range of 10 to the 7 solar masses.
Yes.
So galaxies then, the black holes can't get smaller. They could move to the right.
That's right. Okay.
Yeah.
Yeah,
so
that's a great question. So basically, this is firstly there is scatter around these scaling relations. I just didn't show them for clarity. So the existence of scatter would allow, mathematically that would allow the black holes to basically be more or less massive, even though they are kind of like brighter than this luminosity limit. So this is just a statistical argument. It doesn't mean that if a black hole is this bright, they can never be more massive or less massive compared to the scaling relation. Yeah, but yeah, I guess right. That's just a statistical result. I don't think you can make any inferences about individual objects' history just based on this statistical predictions. Yeah.
Hi, Haowen. Great talk. So I have actually two questions which
Yeah.
are kind of linked to each other. So, and that is essentially about the numbers. So the first question is so where does the scatter come from in your model specifically? And second,
Right.
So obviously if you have a selection bias that you only see the brightest ones,
Yeah.
then depending on how big the scatter is, the number density of these will be very low.
Right.
So, however, from James Webb, which have these very small fields, it seems to suggest that the number density of this object is very high. So, does that match what you have in your model? Thanks.
Yeah. Great. That's a great question. Two great questions. Firstly, the scatter. There is scatter in the scaling relation between black holes and galaxies, and how are they constrained? Basically, they come from let me get back here. So they basically come from the shape of the active black hole mass functions. Because if you have a larger scatter around this scaling relation, it would basically increase the amount it leads to an Eddington bias, right? So it would just increase the number of massive black holes and flatten the active black hole mass function. Okay, so here we do have to assume that this scatter is redshift independent, given that we don't think we have enough data to constrain the redshift evolution of this scatter. So we do, like in the paper that we're writing right now, we do seem to see that the number density, well, I should say that the absolute number density doesn't seem to be too crazy for us, comparing JWST observations and our prediction. I think what seems quite off to us is that in what kind of galaxies do these quasars exist? They seem to be too frequently appearing in low-mass galaxies compared to our predictions, and that's something that we are currently working on. Yeah. Thanks.
Okay, let's thank all the speakers in the next session. We now move to the discussion led by Mark and Aaron.